For this problem, we have the following circuit diagram, and we are asked that given the phasor voltage VGT is equal to 50 cosine 100,000 times t volts, and we're going to use this information to find the power average for our voltage source. Now, it's asking us to find the average power absorbed or delivered by the voltage source. This is very key because it can be either being absorbed or delivered. And if we look in section 10.5, power calculations, that specifies this, we're going to see the first thing is that usually a source is supplying power, and thus the current is in the direction of voltage rise. For it to be absorbed, our current needs to be in the same direction as our voltage. For this to happen, it needs to be in the direction of our voltage drop, not the voltage rise. So currently, for this voltage right here, the actual voltage direction is from the positive to the negative. That is the direction of voltage drop. Now the actual current flowing through here is going to be into the positive through the negative. So opposite direction. Since it's an opposite direction, we need to have it being delivered instead of absorbed. So our answer will have a negative. To find our power, we're going to look to the notes linked in the description below the like button, section 10.1, instantaneous power. In here, we have the following formula, and we are going to use this. We know our Vm, this is given to us as 50. The only thing we don't know in this formula is our Imax. So now we are going to find it. To find it, we are going to use Ohm's law. Ohm's law states that we have our current is equal to our voltage over the resistance. And the resistance is equivalent to impedance. Now, impedance is what we need to find. So to find impedance, we are going to combine all of our impedances together. First thing that I'm going to do is combine these two impedances in parallel. Once we do that, all of the other impedances will be in series, and we can simply just add them together. So before we start, I'm going to need to convert this capacitor to the impedance form. So this is going to be our ZC is equal to a negative J over our omega times C. Our omega in this case is 100,000. So we're going to have negative 1 divided by parenthesis 100,000 times our 1 times 10 to the negative 6. The reason why we're multiplying by 10 to the negative 6 is so we can get this in farads instead of microfarads. This is going to be equal to a negative J times 10. So that is our capacitor. Now we're going to solve for our inductor. For our inductor, the impedance is Z of L is equal to AJ times our omega times C. Our omega is going to be the same, 100,000, multiplied by the 50, multiplied by 10 to the negative 6. And this is going to give us a Z of L of J times 5. So we need the parallel formula for impedances. This is going to be 1 over our first impedance plus 1 over our next impedance, all raised to the negative first power. Now we are going to solve for this. Once we do that, we are going to get this equation. We want to simplify this further, so we're going to multiply this by 5 minus J times 5. This is going to be the rectangular form for the two impedances in parallel. Now we're just going to add them to the other impedances since they're now all in series. So for series, we are going to have our 1 microfarad. This is our negative J times 10. We are going to have the next impedance, which is what we found. This is 2.5 plus our J times 2.5 plus our last impedance, which is the resistor, and this is 7.5. Now, if we add all of these together, we are going to get 10 minus J times 7.5. And this is our total impedance. Now we can plug it into our Ohm's law, which we read out earlier up here. Our I is equal to the voltage, which is 50, and this is being divided by our 10 minus J times 7.5. Now the easiest way to solve this is to put it in the polar form. In fact, we need it in the polar form because we need the angle and the max for it for this power equation here. And to convert this from rectangular to polar, we're going to use the following equation. We have Vm is equal to the square root of our real number squared plus our imaginary number squared. We have the angle equal to our tangent negative 1. And then inside of here, we have our imaginary number divided by our real number. So we are going to use these formulas. This is going to be the polar form for our equation. Now we want to check if our angle is correct. So when we graph this, our imaginary number is in the y-axis, which is in the negative. Our real number is in the x-axis, which is in the positive. So that means our angle has to be in the fourth quadrant, which it is. So we know that we've done this correctly. Now we're going to take our numbers, divide them. We are going to take our denominator angle and subtract it from the numerator angle. And for this, we are going to get 4 with an angle of 37 degrees. So this is going to be equal to our Imax. And we are going to use this and plug it into our equation. So we have a 50 times 4 Then we have a cosine of our angle voltage minus our angle current. We know that our angle voltage is 0 because we don't have it in our original equation. So we have 0 here, and then we're going to have our 37 degrees here. We found everything. So now we just need to plug this into a calculator as 50 times 4 divided by 2 times cosine. Make sure it is in degrees. Your calculator has to be in degrees with a negative 37 degrees inside of it. This is going to give us approximately 80. So this is what our power should be. If I reveal this, I can see that's a negative 80. Remember earlier when I said that our voltage has to be a negative? So this is why our power is now a negative. That's how you'd go about solving for part A. Now we want to solve for part B. The formula for this is also in the notes linked below the like button. It's going to look like this, where we have this equation. We're not trying to solve for the P. We're not trying to solve for any of this. We just want the Q. So now we can plug our values in. We know that our Vmax is 50. We know that our Im is 4. Our angle of V is 0. And our angle for the current is a 37 degrees. So all we need to do is plug this into a calculator. Is a negative 50 times 4 divided by 2 times the sine of our negative 37. And if we do this, we are going to get that RB is 60 degrees. That is how you would go about solving for part B. Now for part C, we need to find the apparent power. So we're going to look in our notes again, different section though this time. We are going to be looking at section 10.4, complex power. One of the first formulas that we see in this section is the apparent power formula. It's going to look something like this. Now all we need to plug in is what we know. We know that our power is equal to a negative 80. So this is going to be squared, and our Q is going to be the 60. So in our calculator, we're going to plug in the square root of our negative 80 squared plus the 60 squared. This is going to give us 100 as our answer, and that is how you would go about solving for this problem. If you want notes that cover this topic, again, they are linked in the description below the like button, and if you want more network analysis problems, there's a playlist in the description as well.